So, welcome back. I hope that you enjoy the last lunch of the Hure 17th edition. So we are going to enter in the last panel of the day and also the last panel of the conference. This panel is about quantum computing and its applications, and it will be chaired by Pep Martorell, but for those who don't know him, he's probably no one. He's the Associate Director of Barcelona Supercomputing Center. So, Pep, whenever you're ready.
Yes, that's fine. Thank you very much, Alberto. My role here is just to chair the session and introduce all the people and try to explain a little bit what we're going to do, we're trying to do here. This is probably the most complicated session of the conference because it's about quantum, which is always a little bit, fuzzy, because it's the last day and it's after lunch. So probably everybody's a little bit, waiting for something a little bit exciting. We will try to excite you with all the people we have here. We've been talking during this conference about, I think, the hottest topics in HPC today, about RISC-V, about AI, about energy. Now it's the time to talk a little bit about quantum, its integration with HPC, its applications, etc. Our objective for this panel is basically we have two objectives. First one is trying to put everybody on the same page. Yesterday during dinner, I was talking to some of you and some people were saying, okay, I don't know anything about quantum, or I'm a real expert about that, how we can manage this situation. Fine, the first person to talk today is Artur. I will introduce them later, just in order to make something like an introduction to quantum computing for everybody. So probably some of you will already know everything that Artur will explain, but some not, so we will try to put everybody on the same page. And after that, the idea is to share the vision of the future of quantum computing and its integration with HPC, and we're going to talk about infrastructure, architectures, and also training, learning, teaching, how we can boost all the ecosystem by training in this discipline to more and more people. Let me just introduce briefly all the people that today are going to talk. First of all will be Dr. Artur Garcia. Artur is the director of the Quantic Research Group at the BSc. He holds a PhD in quantum information at the Photonics Institute, a postdoc in Stony Brook, and his research is mainly in the interface between quantum algorithms, machine learning, and these type of things. And he is the one I have asked to present a little bit, to introduce a little bit the quantum things, the quantum computing to everybody. After Artur, I think, is the time for Alba. Dr. Alba Cervera has a PhD in physics by the UB, by the University of Barcelona. After the PhD, she moved to Toronto, where she carried out a postdoc in quantum computing. And since October 21, she's senior researcher at the BSc, and she's also the coordinator of the Quantum Spain project. After Alba, we have Carmen Almudever. Carmina, I think, yeah, could be, okay. Carmina holds a PhD in electronic engineering also from UPC. She's been, moving in many places, in Delft, collaborating with Intel, and since February 21, she joined the computer engineering department at the UPB, Polytechnical University of Valencia. And last but not least, Elias Combarro. He has a PhD in mathematics, has been associate professor, computer science department, also at the University of Oviedo. A lot of papers published in different journals in topics such as computability theory, machine learning, and he's co-author of a book called A Practical Guide to Quantum Machine Learning and Quantum Optimization. And this is mainly why we've asked him to talk about how to train people about quantum computing. So, without more introduction, I will give the floor to Artur, and after that we're going to call a little bit the rest of the people to talk about infrastructure, architecture, training, and of course, any question, very well welcome at the end of the session. Right, Artur? Your turn.
And then I can move things with this. Is this working? Yes. Okay, good. First shot. Thank you. So, hi everyone. I'm Artur Garcia. I'm.
You can move a little bit, right?
You're fine. I mean, don't worry.
Yeah, but you feel a little bit observed by everybody.
Okay, how long do I have? Like 25 minutes?
Could be 20 by
20 is fine. Okay, so I'm Artur. I'm in charge of the quantum computing group at BSc, which is a group of research about 15 people. It has been working for the last 4 years here. And I have the honor to talk about, to introduce quantum computing, okay? Which is I always fail doing this because there is people in the audience who are physicists, and then of course I'm boring them. And then there are computer scientists who are, I think, the ones that have to work with these machines. And I mean, I cannot put like all the equations of quantum mechanics here in 20 minutes, okay? I'm sorry about that. So I will try a different thing. Let's talk about computers. We are experts on computers. So let's start from the beginning of our lives with the first computer that you ever had access to, okay? Which is this thing, okay? And whenever we think about computers, we think how to use them, okay? So we can perform like mathematical operations with this computer. And my first question is, how many numbers can you count with your hand? Okay? And this is like, when you realize about this, the total failure of the education system, because we are taught all our lives to count up to 5, when this is a very powerful device that can be, this is not working. You can use this device to count up to 32, okay? How do we do that? I mean, we have binary codification, and we can use binary numbers with our hands in order to give more power to this device, to this resource, okay? And this is actually the interesting thing. You have to be always aware of the resources that you have at hand and what kind of problems can you solve with these resources. And actually, this is the current status of quantum computing. We have to solve these problems. Oh, by the way, this is, I think, very important information. With 2 hands, you can go up to 1,024, okay? And then this goes increasing and increasing exponentially with the number of fingers, okay? So this is an important thing. We have to be, as computer scientists, aware of the resources and use these resources to solve problems, okay? So this is basically what quantum computation is trying to do, but with a different family of resources, with quantum resources. So the story shouldn't be that different, at least in principle. Then experimentally, it's a different story. But at least up to here, the quest is the same. We are going to have different resources, and we are trying to solve problems with these resources. Okay? We are computer scientists. We are also physicists sometimes. But now we have this word quantum in the middle, which may be annoying sometimes. Okay? So let me explain a little bit about quantum, and let's see if we can manage to understand how to use these resources to solve computational problems. So first of all, what is quantum? Why do we use this fancy word, quantum? Okay? Quantum mechanics is a theory that was developed at the early 20th century to explain a lot of different experiments that for the first time we were able to do in the lab. Okay? And these included very exotic problems, like how to describe the internal structure of an atom, how to describe light. Light is a very complex thing to describe, and actually it's a quantum system. What happens when you work at very low energies? We were able for the first time to reach very low temperatures. And when you cool down things, they behave in a very weird way. You have superconductivity, you have superfluidity, which are things that we were not able to explain with the current theories at that moment. And then we have the interaction between light and matter. Then it's even more complex because you have all these quantum systems and they have to interact. And then, of course, you have emerging new phenomena coming from these purely quantum effects, okay? And these, the most important ones probably are the laser and the semiconductors. So we have all this new theory, and it's very handy and useful. And the question from the very beginning was, okay, engineering all these technologies is going to be very hard because these are very delicate systems. These work at very low temperatures in all these extreme conditions, okay? Very low temperatures, and whenever you have isolated single atoms or single photons, okay? So let me explain a little bit in one slide what the quantum theory is about, okay? And this is actually how everything started, with a very simple model of the atom that we are going to use in order to process information, okay? So whenever we think about the atom, it's very similar to the solar system. You have the electrons just circling around the nucleus, but actually it's a valid picture. It's slightly more complex. But the idea is that we cannot put electrons wherever we want. There are some rules that come from the theory that will tell us that the electrons can be only on these orbitals, okay? So let's forget about large atoms, and let's focus on a very simple atom that only has one electron, okay? And this electron is in a particular orbital just moving around. Whenever we want to move from one orbital to the other, we have to give energy to the system. And we can do it in many different ways, but one very useful way of doing so is to just shine some light, some laser light into this atom. And then the electron will capture this energy and will move to another energy level, okay? It makes a jump, okay? Actually, it cannot be any jump. There are very strict rules on which jumps we can do, according to the structure of this atom. And this means that the frequency of the light that we can use to make this transition is very peculiar. It has to be very precise tuned. Okay? Whenever the electron is bored of being in this orbital, he can jump back again to the inner orbital. And by doing so, he will release the same amount of energy. Okay? He's giving back the energy that he captured to move to a different orbital, and he will release the energy. We've seen this many times. Every time you see one of these neon lights, this is the phenomena that you are observing. Okay? So actually, we already have our first quantum computer here, because we are going to use these kind of effects. We are going to choose several of these orbitals in order to label the information. We are going to say, okay, if the electron is in this level, it's going to be a 0. If it's in another level, it's going to be a 1. And actually, we have how to operate this quantum computer by means of light. Okay? We are going to use laser light. And actually, this explains a lot of things that we are used to see all day long, because this explains how the atoms work and also how it is the interaction of matter with light. So by a follow-up of the quantum theory, we have already a quantum computer. Okay? Of course, if you go to the lab, things are much more complicated. But at least I'm happy with the theory. So what's weird about the quantum theory? The quantum theory is very different from other theories that we used to have in physics, because it's whenever you set up the experiment and you repeat the experiment under perfect conditions, the experiment not always behaves exactly the same. Okay? This, at the beginning, was considered to be a flaw on the theory. There was a problem with the theory. The theory was not complete, and we didn't have control over all the degrees of freedom of this theory. And then, of course, there was some emerging probabilistic behavior. But of course, after many years, we discovered that actually the theory is probabilistic by itself, because it turns out that nature is probabilistic. Okay, in a sense. So far, we understand nature at this moment. So the theory is very precise, but instead of giving deterministic answers, we'll give deterministically the probabilities to find a given answer. Okay? So it's not deterministic in the sense that is giving the position of a particular electron at a given time, but it will tell us with very precise accuracy what's the probability to finding the electron or the outcome of some experiments after repeating this experiment. Which means, okay, we cannot find a perfect or complete theory, but we can find with very high precision all these probabilities, which is very nice in a sense. If nature is probabilistic, let's compute probabilities. There is a problem here, and I will tell you why. Whenever we have these probabilities, we only have to store all the collection of these probabilities in order to know about our experiment. Okay? And this is going to be a problem, because collecting all these probabilities is going to be a very hard problem. Okay, but first let me tell you something. You are probably used to this. Whenever we explain quantum computing, we have to explain why do we do things with quantum computers. And the main reason is going back to the origins of computational theory or complexity theory in computational science. Okay? And the question is, there are easy and hard problems. This was observed at the early days of complexity theory or like computer science by itself in the 40s. And I sum up this problem in the following sentence. Running a marathon is harder than running 100 meters 420 times. Okay? So sometimes solving a problem means that you have to solve sections of the problem in advance. And this adds up to create complexity, algorithmic complexity. And then some problems will require an amount of resources to be solved much larger than others. Okay? We don't have a clear theory of why this is happening, and actually there are many open questions here. But the fact is that there are problems which are hard and there are problems which are easy. Okay? Which is good for us, people making supercomputers, because otherwise everybody will solve everything with a laptop. Okay? There will be no supercomputing. But what does it mean? Okay, this is PowerPoint magic, and everything is moved, but you get the idea with this plot. Sometimes when we increase the problem of the size of the problem, the resources that we need will increase exponentially, and sometimes they will increase polynomially. Okay? And this is a very asymptotic way of thinking, but actually it has practical implications in many things that we do. Okay? So the typical example is multiplying two numbers. It's a problem that we manage to do. If we are given two numbers, we can multiply them. If we are given like 25 digit numbers, we know that this will cost roughly 25 more times than a single number multiplication, okay? And I would say that this is an easy problem, okay? It can be very, very large, but as we increase the size, then we see that actually the complexity grows linearly, we can say. So the running time of this algorithm is not going to be very, very, very hard. But if you go to the opposite problem, which two numbers will give you a given answer, that tends to be a very hard problem. Okay? We don't know why. There are easy and hard problems. But this one, in particular, is very hard, which is good because all cryptography is based on this complexity of the problem, meaning that if I give you 26, you may be able to tell me two numbers that multiplied will give you 26. Okay? That you can be doing now, right now, multiplying mentally. But if I give you a very large number, that may be a hard problem for you and for a supercomputer. Okay? And that's what we mean by a hard problem. So if we count how long does it take to make this problem, this will grow exponentially with the size of this number. Okay? So there are hard problems, and we built quantum computers in order to solve some of these hard problems. This is the main idea. Which problems? Let's imagine that I want to store the probabilities of an experiment that will involve only 40 or 50 of these atoms. I want to store all these probabilities together. The fact that they are in a quantum state means that these probabilities regarding the position of this electron will have to do with the probabilities of finding electrons in all other orbitals. Meaning that at the end of the day, I have to store a very large number of probabilities in order to explain the possibilities of all these systems giving a different outcome. And this is a very hard problem because I need an exponentially large amount of numbers to explain a system which is rather small. I mean, 45 atoms is nothing. Okay? This is a hard problem. I cannot put all these probabilities even inside the memory of Mare Nostrum 4. And even if I manage to do so, just by increasing a very small amount of numbers of atoms here, then the problem is out of reach of any supercomputer on Earth. Okay? That's a hard problem. Okay? So why quantum computer? Quantum computing is the actual intention of building devices that will be able to attack this problem by using the same rules that make these problems hard. Okay? And these are quantum computers. Even if we don't manage to build quantum computers, there is an interesting feature here, which I like to describe with this sentence. Computer science is no more about computers than astronomy is about telescopes. Okay? Quantum computer is an idea or a new paradigm to think about computational complexity. It's not only a thing of building quantum computers and solving problems with these devices. We need to think about computational complexity in a different way, understanding that there are resources that go beyond the model of the Turing machine, the classical Turing machine. Why? Because the Turing machine is a subset of the quantum computer. We can do exactly the same operations with a quantum computer than with the Turing machine, which is a regular von Neumann architecture, but also we can do something else. Okay? So from now on, the idea is, at least at BSc, we have a clear vision of how to use quantum computers in order to solve problems. And which problems we want to focus on? Problems basically of a scientific nature. We think that the first applications of quantum computers are going to be scientific problems related to physics or material science, chemistry, problems that have an internal description based on the quantum theory. Okay? But also, we are going to use the idea of building or having all these devices and use them for making computations. Okay, so in order to build a quantum computer, you need a system that will behave according to these quantum rules. Okay? And remember, these rules appear in a system when it's a very low temperature or it's a very reduced number of elements, of atoms, for instance, or photons. So there are many proposals of different technologies in order to build a working quantum computer. And these include, for instance, using light. Light is very, very cheap. You turn on the light and there you have like zillions of photons that can be used potentially to make computation. They have, of course, many technological complications, in particular how to make them interact quantumly. But also you can use ions, because ions is just atoms which are ionized. They have an electrical charge, and they are very handy in order to be moved around by electrical fields. Okay? So technologically, you can solve some of these problems with one of these approaches, with one of these architectures, but then there may be other problems. And the preferred choice in the field right now is to use quantum circuits, which is basically electronic circuits that put at very low temperature, they will start behaving in a quantum way. Okay? We need the quantum theory in order to explain the charge and capacity of these quantum circuits. Why is that? Because whenever you work with ions, you are restricted to the architecture that nature has already built. These ions are nature products, okay? While if we use quantum circuits, we are designing these circuits to have particular frequencies that can be tuned to the electronics that we are using in the lab. So this is technologically, it's a very more useful approach, or more handy in the lab, in order to design something that can be used, because we need to program these devices and use them regularly and be able to repeat the experiments. Okay, so there is an interesting discussion here, is how powerful are these devices? How powerful are quantum computers compared to Mare Nostrum 4, Mare Nostrum 5, or Mare Nostrum 25, okay? So, and there is also a discussion about how far can we reach with computational devices in general, okay? So let's think about something. Most of the problems that we consider to be hard are going to be hard because our computing device is either not powerful enough, or because this problem is hard and we will never be able to solve this problem. And this is a fundamental limitation that we may be able to address with this discussion in quantum computation. Some problems are never going to be solved even in nature. So there are problems that will never, for instance, thermalize, or we may not have all the information to solve that problem. Okay? And also because if we prove that actually quantum computers are the most powerful computing devices that we are able to go in to build according to physical limitations, that may be that the quantum computer is the ultimate computing machine that we are going to be able to build. Okay? Meaning that every computing device is based on some interactions, some physical interaction that is happening inside, which is actually doing the computation for ourselves. For instance, when we use a normal computer, we are assuming that there are some electrical interaction between the electrons in an electric circuit. Okay? The same thing happens with the interaction between quantum particles based on this quantum theory. But if we think that actually this quantum theory is some sort of ultimate theory that explains everything that happens in the universe, the quantum computer is the computational paradigm using the more advanced theories in order to design computing devices. Okay? So we may be able to face a situation where we discover that problems that cannot be solved with a quantum computer are never going to be solved. Okay, okay, so there are these two different technologies, and sometimes we see them as very different, like quantum on one side and classical on the other. We use, by the way, we use the word classical to refer to everything that is not quantum, okay? So it's not like we refer to a computer built on 2,000 years ago. It means like a supercomputer is a classical device, okay? So at BSc we have this project where we try to put these two technologies working together, okay? And this is in line on the European, probably Alba, you're going to explain about this in more detail, but there is this vision in the European level to have supercomputers sitting side by side with quantum computers. Why is that? Because on one hand, we have the more powerful advanced computational devices in like supercomputers or clusters. In the other, at this moment, for operating quantum computers, we need the help of classical resources. The quantum computer at this moment is not going to be a standalone device that is going to work by itself. It's going to be helped by pre and post processing done in the classical side. This is going to be the integration of these two technologies is going to be the task for supercomputing centers for the next years. And it's a very interesting project that will happen here at BSc and in other supercomputing centers in Europe. Yeah, 5 minutes, okay. So what do we do at BSc in particular? So we do fundamental research in quantum computation in the sense of designing new algorithms for particular problems that we identify that can be hard for a supercomputer, but could potentially be easy for a quantum computer. This is the million-dollar question, or the billion-dollar question. Everybody's looking for these kind of problems because it's actually going to drive a new field, a new industry, in order to develop these devices to solve problems that may create like interesting solutions. So for that, we are going to have a research team that I will introduce later, but we are also going to have, funded by the Spanish government and also the European Commission, the installation of 2 actual quantum devices. They are going to be installed here at BSc and operated by the BSc operation system. There is also knowledge transfer. There is patents, companies involved in this, and we have a close collaboration with the industry, the local industry, in order to bring all this knowledge into applications for them. This is not something that should be restrained on the research level. This should be spread and have applications for companies and in the local ecosystem. Okay? So we collaborate in training and recruiting activities. This is very important at this moment. We need to form people that will operate all these things and will develop these further. And we need a lot of manpower for that. And then, of course, the national program that Alba is going to talk about in a second. So this you can explain much better than me. So in addressing the fundamental problems in quantum computing, just to finish, we designed these quantum algorithms for complex systems, and the nice word here is complexity. How to address all these different computational models related to complex problems. Okay? And then, as long as we don't have very powerful quantum computers, an interesting direction in supercomputing centers is how to simulate a quantum computer. And this is a very hard problem by itself that we can use like a supercomputer to do up to some point. And then we have to design new numerical methods that will be running on a supercomputer, mimicking the behavior of the quantum computer. And this is some active field of research now because it's becoming an important problem in order to understand what happens inside a quantum computer. Okay, so I can skip this. We basically work on the algorithmic side. We simulate quantum systems, but we also collaborate with experiments. And this is very important. We don't want to be very away from what is happening actually in a real lab. We have to be aware of the limitations. There are many imperfections in quantum computers that can also benefit from the simulations that we run on the supercomputer. And then the kind of problems that we may be addressing first, we don't think about the quantum computer as something that on the first iteration will be solving any kind of problems. And this is an important thing. We are trying to be not that ambitious as we were in the early days of quantum computing and trying to identify problems for which we can create particular instances of a quantum computer in order to address these problems. And the best example for me is optimization. Optimization, of course, is a very important problem. There are subfamilies of optimization problems that can be addressed easily, let's say, with a quantum computer. And the main limitation that they overcome is that we don't actually have to compute gradients in order to optimize these functions. So we have a gradient-free method for optimizing polynomial functions, which is of a very wide application in many engineering and scientific fields. Okay? And this can actually be done directly with one of these quantum devices that are already built. So these devices, they are like super tiny, they are operated at very low temperatures, but they are already happening. I mean, quantum computers already exist. They are not very powerful, but they are not like a science fiction thing of the future. Okay? They already are existing in many different labs. Okay? And there are many already happening pilot programs where important companies are trying to test this in their already infrastructures. And the interesting thing is to help them, and this is something that we do here, in order to give an idea of what's the impact of this technology in their field. Okay? Because they have optimization problems, they have like scientific problems sometimes, which are very fundamental, and they have to be aware if this technology is going to have an impact on their work. Okay? But of course, the last application is like the promised cryptographic impact of quantum technology as a technology that has the potential to break cryptographic keys in polynomial time. And this is probably the most important promise, which look always very far in the future, but according to the roadmaps that some of these companies developing quantum computers are already publishing, this could be at hand in the next 10 years. We've been saying this for the last 20 years, okay? So it's difficult to say that this is going actually to happen. It's like a moving goal. But actually, the interesting thing is not what they promise in the far future, but what they have been promising for the last 3-4 years. And actually, they've been very good at keeping on their path, okay? So that makes me, I mean, not super optimistic, but at least that may be the right time to say that in 10 years we're going to have this. Okay, so I finished with this. Thanks a lot. Of course, this is the team. Okay, we have a team which I like to mention. It's formed by physicists, of course, but there are many people who are not physicists. And actually, this size the size of the group of non-physicists in the group is increasing, okay? So I think that at this moment, it's going to be very important to recruit people from other fields with some training on of course, on the quantum theory, but actually they can bring a lot of things to the quantum computational field without being physicists. This is something that we have to start like thinking differently. And that's it. I'm finished. Thanks a lot for your attention.
Thanks, Artur. I think it's work. Yeah. Probably one of the main takeaways of this is that it's not a matter of classical versus quantum, but classical plus quantum. But now we think that we have at least 3 main challenges, and this is why we have 3 people here just to intervene next. One is, how are we going to buy and to install and to operate a system like that in an HPC center? A second challenge is how are we going to use, how are we going to program, what about the architecture, etc., the full stack of these systems. And the third challenge is how are you going to train people to be able to use these systems in one of our network in our centers. So I will give the word now to Alba, which is the first, trying to solve the first challenge, which is how are we going to install, buy, acquire, operate machines like this, right?
Okay. Ah, no, al revés. Sí. Ah, no, Carmina. Sí. Sí. Mira que estoy. Oops. Perfect. Okay. Thank you. So yeah, I'm going to explain a little bit what is the view of supercomputing centers, especially in Europe, with this new paradigm of quantum computers, and especially how are we going to integrate them into our infrastructure, and how are we going to share it with everyone and all the users interested in this technology. So first of all, the main message is, sometimes, I mean, I think that we are passing this way of thinking, but supercomputers do not compete with quantum computers. So quantum computers are becoming some partition of these supercomputers, because in the end, as Artur was explaining, there are some computational problems that supercomputers cannot achieve, or the scaling is really bad, and that's why we are developing quantum computers in the first place. But there are other applications that we don't really need to develop this power in computation, so we can continue using supercomputers. And on top of it, there are no standalone quantum computers, so we really need classical computers and standard computers to control, to design, to execute even programs in quantum computers. So the vision that most of the field has is the following. So we, as a user, I will design an algorithm, and depending on the computational power that I require or the type of algorithm that I'm targeting, I will use it in a GPU, in a CPU, or in a quantum processing unit or a QPU. So it is natural to install these quantum computers, the ones that are more advanced prototypes, in supercomputing centers like ours, because in the end we have experience in integrating very sophisticated computational systems, and on top of that we have the proper infrastructure to share the resources to all the users that are interested in this technology. So the flow, the moment is the following. So of course we are talking about very novel technologies. So although quantum computing has been around for many, many years, has been in the last 15 years or so that this has been developed much further, especially in the experimental side. So that's why there is still a lot of research to be done to improve the technology and to improve these quantum computers and also trying to overcome the errors that they have or to scale them up. So we need research, and this is happening in universities and research labs that are building these prototypes of quantum computers. But then what happens once these prototypes are more advanced? Then we need industry that develops these prototypes and scale the TRL of all of them. So supercomputing centers can come and can buy these devices from these companies. So we are in the last step, so we are looking forward to buy these devices from companies that develop them, and that's why we need first the research to be developed, and that's why we also sometimes collaborate with research labs, because we try to understand what is the capabilities of current term computers. So in particular in BSc, we have two main programs to acquire these quantum computers. One is Quantum Spain, which is the biggest one. It goes directly to the Spanish Supercomputing Network, and it also has the participation of another 14 institutions that I will show the map now. And the goal of Quantum Spain is, first of all, to deploy a digital superconducting circuit quantum computer. That means that we are installing this device in the BSc. So basically, once Mare Nostrum 5 starts operation, we will start installing the quantum computer in the chapel. And then we also develop quantum emulators. That means simulators that run on standard supercomputers in BSc, in Thesga, and in Skyle. Of course, the main goal is to share all these resources with all the users. So we are creating all these access protocols that will follow the same structure as standard supercomputing protocols. And we also collaborate with all the research institutions to develop novel quantum algorithms and also for training purposes. But besides Quantum Spain, we are also part of the EuroQCS Spain project, which is another European project that basically focus on the integration of quantum computers with supercomputers. And I will explain about it later. Oops. So talking about Quantum Spain, as I was mentioning, we are installing a quantum computer of technology superconducting circuits. We are defining the access through the Spanish Supercomputing Network, which means that basically in all the nodes of the Spanish Supercomputing Network, there is a trained support technician that knows about quantum computers, that knows about what are the capabilities of the device that we will have, so to assist the users and to help the users to adapt to use the machine that we are installing there. Then, of course, we have research with another universities and research center. And finally, we are creating the Talent Q program, which is a big training program to help and to explain to people how to use quantum computers and for which purposes. The partners of Quantum Spain, as I was mentioning, are 27 right now. So we are very happy to finally welcome everybody that knows about quantum computing, or mostly everybody that knows about quantum computing is participating in Quantum Spain. And we are looking forward to share the research and the codes that we will be developing with all these partners, with all of you. And finally, these are my final slides. The selection of, so there was a very big call from EuroHPC to host, to finding the hosting entities for European quantum computers. That means quantum computers made with European technology and which users will be the European users, so people that belong to the European countries. And Spain was selected. That means our center was selected together with the other 5 in Czechia, France, Germany, Italy, and Poland. And our vision is to acquire a different type of quantum computer and to integrate that into Mare Nostrum 5. So basically, you as a user, you will come to BSc and you will have access to a digital quantum computer, an analog quantum computer, and of course, the general purpose and accelerator processors from Mare Nostrum 5. And in the end, this is a very complete infrastructure that will also be shared with the rest of European users. And the other hosting entities are targeting other types of quantum computing experiments and platforms in order to have the most variety of applications. And finally, this is my final slide. The main idea of Europe is going to the EuroQCS, the European Quantum Computing and Simulation Infrastructure, which is basically creating this very big network as it exists in supercomputers, but with quantum computers, installing them in the supercomputing centers in the Union. So we are now in the first phase of this EuroQCS, so I expect that in the following years, you will have access to all types of quantum computers together with supercomputers in all these centers that are part of the network. So I think that's all from my side. Thank you.
Thank you, Alba. I'm now going to give the word to Carmina. I would like to know, after these interventions, I would like to ask to Uriol Pineda to explain a little bit to the users here how they're going to be able to use these systems. Because as how Alba has said, that there will be one quantum computer, there will be 3 emulators at least, All of them will be available through the REST procedures. We have a lot of REST users here, so Uriol, after all these people, probably it's your turn to explain how exactly this is gonna run in the future. I prefer to alert you before just asking directly.
So thank you very much. Good afternoon to everyone. I'm Carmen Almudever from Technical University of Valencia, where I lead a group on quantum computing architectures. Before talking about quantum computers, I would like to thank Per Martorell for having invited me to this event today and share with you my vision and my experience on quantum computing. So although Artur said that quantum computing is not only about building quantum computers, I would still like to talk about how to build a quantum computer, right? And what is the architecture of the kind of system of full stack that we have there. More specifically, I would like to start by giving, let's say, reviewing the progress of this field, that I think that has been remarkable in the last years, moving from something theoretical to something experimental that is already a reality. And also talking about the challenges that we have there and what is going to be, how this system is going to be look like in the near future. So first, let me emphasize, this has been mentioned before, we tried to think right. At the end, we didn't manage. We prepared the slides at the last minute, right? So I would like to maybe repeat some of the concepts that has been already shown before. So let me again emphasize what a quantum computer is not. What is not, a quantum computer is not going to be a replacement of classical computers or supercomputers, because they will be good at solving some specific problems. Yeah, not all problems have to be solved by this kind of machines. And although we keep on saying quantum computers, I like to say that what we actually are building is a quantum coprocessor or quantum accelerator, and has been shown before by the pictures of ALBA. So as we have nowadays this kind of heterogeneous systems, where you have the main CPU, right, talking to some coprocessors or accelerators being an FPGA, a GPU, a TPU, and at some point this quantum accelerator or quantum processing unit that was mentioned before. Therefore, what we are building from an architectural point of view, it's a hybrid system in which you have the full stack of a classical system talking and working together with a full stack of a quantum machine. So, say that, let me revisit the progress. Oops, what did I do? Coming back, yeah. I just pushed the wrong button. Yeah, we are back. So I was saying, let me review the progress of this field in the last years. So the idea of building a quantum computer is not new, but was already proposed back in 1981 by the physicist Richard Feynman in the conference, The Physics of Computation, that was in MIT, where he was, in a keynote that he gave, he was asking some questions like, how can physics be simulated by a universal computer? The problem is we cannot simulate the quantum mechanics. So how we can do that is by building a quantum computer. Since then, as I said before, the field of quantum computer has made a remarkable progress with the development of the first algorithms in the early 90s, like the Shor's algorithm for factorizing large numbers, and this is the one used for encryption, decryption, and so on and so forth, and the Grover's algorithms, the Deutsch-Josa, you name it. Then, at the end of the 90s, the first quantum computer was commercialized. This is the famous D-Wave, a company in Canada. This kind of computer is based on a model that is called quantum annealing, so there is a debate if it's a real quantum computer or not, because it doesn't show this kind of promising speed-ups. Then, in the early 2000s, the first implementations of quantum processors or quantum systems start appearing based on different technologies, as Artur mentioned before, based on superconducting qubits, NV centers, trapped ions, quantum dots, you name it. And currently, there are different companies and research institutes that already have this kind of processor, that, for example, being the most famous ones, the one from Google, the 53 qubits device called Sycamore, that was used to prove this quantum advantage. This quantum advantage is a term that is used for referring where a quantum computer solves a task or a problem being useful or not, that a classical supercomputer cannot solve. Then we also have chips from Rigetti, or the ones indeed from IBM. The last one is the Osprey processor with 433 superconducting qubits, or IonQ with trapped ion qubits. As you may know, some of the devices are accessible by the cloud, so users can just program, send the algorithm, and run it on these real devices. Now, nowadays we are Windows is blocking me. Now it's working now. Thank you. So nowadays we are in the so-called NISQ era. NISQ stands for Noisy Intermediate Scale Quantum Devices. Intermediate scale refers to the sizes of the processors that we have nowadays. You say there like a few hundred of qubits. And noisy stands for because we have like very error-prone devices. We have error rates in the order of 10 to the minus 2 to the minus 3. So as you know, so building something reliable based on those devices is very, very difficult. Now, maybe you have seen this picture before. This is a picture of one of a quantum computer based on superconducting qubits. Solid-state technologies work at very low temperatures. That's why this is what we call the cryostat. The cryostat is inside a fridge, and it has different temperature stages. And in the coldest part, 20 millikelvin, we have the quantum processor. And this cryostat is inside different layers of isolation. And there you can see plenty of cables that go to a different, sometimes to even a different floor, when you have this stack with all the devices, classical devices, that are used to operate and to control the qubits. Yeah? At the end, when we operate these devices, what we send, for example, in superconducting qubits, you send just like a microwave signal with a specific amplitude, envelope, and frequency. And that's how you apply, let's say, a gate, or you modify your quantum information and therefore perform computation. So this system that I showed before, what they implement is what we call the full stack. For those who are familiar with an architecture of a classical computer, this is very similar. We just put, like back in 27, like a queue before each of the layers there, right? But this is what we know, is what we follow, right? So this full stack, what it allows, it provides a high-level programming language, usually Python, that those instructions are translated through the compiler to what is called Quasum assembly language. Those are low-level instructions that belong to the quantum instruction set architecture that, through the macro architecture, are translated into a series of pulses that I said before operate in your qubits. So this is more or less what we have nowadays. We have already, let's say, this full stack. We have devices or elements in all these layers, but there are different challenges there. For example, one of the challenges indeed, and this is something that we focus on, is the development of compilers and programming languages and abstractions to the users. Now, other challenges is, for instance, that, as I said before, in order to operate the qubits, you have all these control electronics that are usually placed at room temperature, whereas the qubits work at very low temperature, right? So you have 5 qubits, it's fine to have like whatever number of cables going from room temperature down to 20 millikelvin, but if you have thousands of qubits, you don't have enough cooling power to dissipate all this heat produced by the wiring. And therefore, there are people that are trying to move these control electronics down to these cryogenic temperatures. Anyway, there are plenty of challenges there in building and controlling these kind of systems, but one of the main ones is about scalability. As it was mentioned before, the power of quantum computers require, or to show the power of these quantum computers, require to build systems that integrate thousands or even billions of qubits. And we are now talking about a few hundred of qubits, right? So how we are going to do that from architecture perspective? So this is the roadmap of IBM that was published 1 year ago, more or less. And what you observe here, it's up to now, what we have been doing is integrating more and more qubits on a single processor, on a single chip. But what happens when we cross the barrier of 1,000 qubits? That we cannot follow that path anymore. We are going to what we call to a multi-core architecture that we have been following also in classical systems, right? To having a single processor, you have several processors, and therefore you can perform parallel computing and as a whole system, yeah? But still, there are a lot of challenges there. Challenges because we will need not only classical communication between those different chips or processors, we will also have to include quantum communication. How to transfer quantum information from one chip to the other, which is far from trivial. Just to focus a bit more on this roadmap. At the beginning, what they propose, as I said before, is to have different quantum processors, integrating like hundreds of qubits, one of these Osprey, for instance, and combine them via classical communications. That will allow us to run, for example, different separate algorithms on them, or even to take an algorithm, to cut it, and distribute it. But still, in order to reconstruct the output, you will have to use some knitting, what they call knitting techniques that are very expensive using classical electronics. The next step that they propose is just to have these two chips in proximity and have some direct link that allow to interact, let's say, qubits from different chips. Okay? That will allow, again, to have like more parallel computation that still makes some quantum communication between the different chips, and also to implement some forms of quantum error correction. I will not enter into the detail, but qubits are very fragile, high error prone, and therefore, if we want to implement something reliable, we need to use quantum error correction techniques. But I will not enter on that. I will not spend the details. And ultimately, what they propose is to have several of those and communicate them not only via classical networks, but also via quantum links. So at the end, and this is what they call the goal of IBM, is to build a quantum-centric supercomputers. This is similar to these AI-centric supercomputers that we have nowadays. But you can see how the complexity of the systems increases. Now we are not only have quantum processors, we also have classical processors combined with quantum networks and with classical communication networks. Here we go. So this is again scalability, and building this kind of systems is one of the main challenges that we are facing nowadays. And just to finish, so in order to do so, what we need is to build also this infrastructure. But back in 2019, we started thinking about, with colleagues here at UPC, we started thinking about this problem. And what we need to revisit is also this full stack. The full stack that I showed before is just for a monolithic and single core quantum processor or quantum computer. But if we go to this kind of multi-core or distributed systems, we will need to have like what we call a double full stack, in which we consider not only the computation, the quantum computation part, but also the communication part, both the classical and the quantum. So, and we are very lucky because we recently got this project that is called Quadrature. This is an European project, an open pathfinder that I have the privilege to coordinate, and we had the kickoff meeting in June in Valencia. So we have 4 years from now to build this kind of multi-core distributed system. In our case, what we propose is indeed to have separate quantum cores or quantum processors that communicate via quantum coherent links between them, but also a wireless interconnection classical communication network. Here you have the list of all 9 partners, in which we also have the BSc, Barcelona Supercomputing Center, the UPC here with Professor Eduard Larcón, BSc with Artur, and myself among other partners there. So I think that's it from my side. Thank you.
Thanks, Carmina. While we're waiting for the arrival of these computers, for having them fully operative, etc., now another challenge is how we train our people to be able to use these computers and how we increase the capacity of our community in this type of new technologies. And this is what Elias will try to explain us.
Okay, good afternoon, everyone. Before I start, I would like to thank the organizers for this wonderful meeting, and also Pep Martorell for inviting me to be on this panel. It's really a pleasure and an honor. And as Pep has just mentioned, I would like to talk a little bit about one of the challenges that we face about quantum computing, and it's how to train people. And this is a challenge that I think it's especially relevant in this kind of meeting, a meeting of users of supercomputing resources, for several reasons. The first one is that it has already been identified that, well, in the short, medium term, if quantum computers become a reality, there will be almost nobody that is able to program this quantum computer. So we will have probably by the end of this year, I don't know, these 2 quantum computers here in the Barcelona Supercomputing Center, maybe next year. But we need people that is able to run something on them. who is able to run algorithms, to run experiments on them. And if this scales, if people start getting quantum computers, we need people able to program these computers for practical applications, okay? So this is something really, really important, because maybe we have the hardware in a few years and nobody can use it. Also, I think it's relevant because a few years back, I was in your place, in the place of some of you. I didn't know anything about quantum computing. I had some problems. I used to work in computational algebra. I was a REST user. I was requesting time in the supercomputers. I was getting like 1 million hours, and it was not enough for my applications. So we reached a point in which we thought, well, once that we have a quantum computer, maybe we can run this kind of thing and we can solve our problems. And it was kind of a joke, but in the end we learned that, well, quantum computers are not so far away, so we better start learning how to program them. So I had no formal training in quantum computing. I didn't follow any masters in quantum computing or something like that. I tried to learn quantum computing by myself. And I guess some of you have tried to learn how to program a quantum computer because, well, it's in the news, it's something that is coming, it's interesting, I know how to use, for instance, a GPU. Shouldn't be so different, shouldn't be so difficult. Well, it turns out that it's quite difficult. It's quite difficult, and there are maybe not enough resources, not enough information, or not enough accessible stuff that we can use in order to learn how to program a quantum computer. So this is a problem I've been involved in, or a task I've been involved in for some years now. I teach quantum computing to software engineers at the University in Oviedo, and I have learned several lessons in the process that I would like to share today with you. As I told you, I've been working in developing material to teach quantum computing not only to physicists, even mathematicians. This is more or less easy, but people who have never heard of what is the Schrödinger equation, what is entanglement, what is superposition, this is a little bit more difficult. As two highlights of my work in training people in developing materials, I have shown here this series of online introductory lectures in quantum computing that I gave from CERN in 2020 online. It was they were quite popular. We had like 1,500 people following them online live, and they are quite popular still in the YouTube channel of CERN. It was translated into Russian in 2021, and I've been told that it's been used by universities in Ukraine and Russia. And an expansion of this course, earlier this year, together with my colleague Samuel González Castillo, I published this book, A Practical Guide on to Quantum Machine Learning and Quantum Optimization. And we tried both in these lectures and in the book to follow these lessons that I learned while I taught myself quantum computing. The first one is to simplify the language, okay? So the first barrier for me when learning quantum computing was that I didn't know anything about quantum mechanics. And I didn't know what the Schrödinger equation was. I didn't know how to solve it, but I must confess that even to this day, I don't know how to solve the Schrödinger equation. And the good news is that you don't need to know how to solve this Schrödinger equation to program a quantum computer, no more than you need to know how a hard drive works to program a supercomputer. Okay, so it's exactly the same. In the end, when you talk about superposition, entanglement, the uncertainty principle, you can translate all these concepts into linear algebra. And linear algebra is something that we all know, okay? We know how to multiply a matrix times a vector. This is what a quantum computer does, okay? So when I first heard about the expectation value of a quantum observable, I was like, what? I was baffled. But it turns out that it's just a multiplication of a row vector times a matrix times a column vector, okay? So the first thing that, well, I try to do when teaching quantum computing, and if you want to study on your own, you can do also, is to try to see this from a linear algebra point of view. And many of the things become much, much clearer. For instance, what is entanglement? This is a simple, very simple notion that can be explained mathematically with the language of linear algebra. Okay, so this is my first advice, or my first lesson. The second lesson is to select the topics. I want to give an example of a book that is probably the most cited book in quantum computing. It's the famous Mike and Ike, the Quantum Computing and Quantum Information by Isaac Chuang and Michael Nielsen. When you ask anybody, what is the book I should read on quantum computing? No, this one, okay? I completely disagree. Don't get me wrong, not because I think this is a bad book. It's probably an excellent book. It's wonderful. It has a lot of information. But I don't think this is the first book that you should read, okay? For several reasons. First, because, well, it doesn't follow this idea of simplifying the language that I mentioned before, and also because it's kind of old, okay? This was written in 2000. There is a revised edition published in 2010, but the topics are kind of the canonical foundational algorithms in quantum computing. Shor's algorithm, Grover's algorithm, Deutsch's algorithm. These are very, very important, but maybe this is not what you want to learn today. It depends, okay? I teach several different courses at the university. In one of them, I tell them about super dense coding, quantum key distribution, Deutsch's algorithm. In the other, I only talk about quantum machine learning, quantum optimization. So it depends on your audience. It depends also if you are learning quantum computing and what you want to do, what are the applications that you intend to accelerate with quantum computing. So nowadays there are many, many different topics, okay? So you should try to go for those that are interesting to you, okay? So we shouldn't try to follow the historical development of quantum computing anymore, I guess, I think, okay? Another lesson is that, well, there are many, many, many different tools now that you can use in order to get some intuition of what is happening at the quantum computer. Well, some intuition. Quantum computing and quantum mechanics in general is not intuitive at all, but at least if you work with just one qubit, you can kind of visualize what is happening with this state of the qubit, how it is rotating in this famous block sphere. And there are many different very good free online tools to do this. For instance, this Quirk, I use it a lot also to teach my students how simple algorithms work, but also the software that is provided by vendors and builders of quantum computers like D-Wave or IBM is quite good in order to get information of what is happening in the quantum computer, okay? So if you try to learn quantum computing just by reading papers, just by reading a textbook, this is good, but it's better if you use these tools to get some intuition to play around. For instance, with Quirk, you can just drag and drop some of the gates and see the immediate impact of these operations on your results. And then you can get an intuition. You can play and say, oh, what if I change this operation, this gate, to a different one, and you immediately see the answer, okay? Connected to this, and even more important, is to code, to run programs. I was absolutely blown away by the fact that all the textbooks that I was reading when I started studying quantum computing were only about asymptotic behaviors, about convergence of algorithms, but there was not even a single line of code. And quantum computing, from my point of view, has to be about quantum, but it has to be about computing. You have to run a program on a computer. Okay, so when we wrote our book, we tried to explain every mathematical detail. My colleague and I are both mathematicians, so we love formulas. We love to explain what is behind, under the hood. We don't want a book of recipes. If you want to do this, just run that. We explain the mathematics, but then we illustrate it with code. And this is something that you can now do, as Carmina mentioned, with several different quantum computers that are available online, with quantum emulators. Here at the BSc, there will be quantum emulators. At the rest, there will be quantum emulators thanks to this Quantum Spain project, and there will be access to quantum computers. And you learn by running. You learn by trying different things and to try to put into practice the mathematics of quantum computing by running code. So to me, this is very, very important. And for instance, this Chuang and Nielsen book has not a single line of code. It was written in 2000, of course. There were no software libraries for quantum computing, but now we are in 2023, okay? Finally, the fifth lesson is to be realistic, okay? There is a lot of hype about quantum computing, okay? It will transform the way we do science. It will change our society forever. It will cure cancer. It will help solving the climate change. Well, maybe, but the truth is that nowadays there is not even a single practical problem, real-world problem, that you can solve with a quantum computer better than with a laptop that you can buy on MediaMarkt. Okay, that is reality. And if you know this and you start studying quantum computing, your expectations are lowered and more realistic. This is a screenshot from an article I published last year in the journal Telos, which is from the Fundación Telefónica. It was later featured by BBC.com, published online also by BBC.com. It's about the myths and realities of quantum computing. And I believe that quantum computing will be something big. It will change how we solve certain problems. It has been mentioned before that quantum computers cannot solve every problem, are not faster computers for every problem. They will solve certain problems exponentially faster than classical computers, but they are not useful for every problem. So when you know this, when you go into quantum computing, knowing that, well, they are not magical devices, there are devices that will be useful for certain tasks, your expectations are more aligned with reality. Okay, so I think this is the 5 lessons we've tried to use to develop all this material, these courses that I teach at the university, the book. And I think that for someone, a user that wants to learn about quantum computing, how quantum algorithms can help solving real life problems, this can be useful. This is a challenge. It's not easy at all to learn how to program a quantum computer, but I think this is something that we need to do with the help of also the Quantum Spain project that has this branch devoted to quantum training. This will be easier, and I hope that if you try to learn quantum computing, you find this advice helpful. Thank you very much.
Thank you, Elias. I would invite my colleagues to join me here. I think we still have 10, 12 minutes to comment wherever you want. While you're thinking of your questions or your comments or whatever, I would like to ask Uriol if he can explain a little bit how this will be managed in terms of the rest users accessing to the future quantum computers in the Spanish Supercomputing Network.
Okay, so
if there's something to be explained.
Well, we can already say some things. So thank you. You have seen here that soon we will have 2 quantum computers in operation and 3 emulators. And the idea is that both of them will be accessible through the Spanish Supercomputing Network. So they will follow the same HPC calls. We consider them other systems that will help solve scientific problems. So the idea is that the the main access mode will be through these quadrimester calls that we have, with the same evaluation panels, with the same objectives. And then we will have also an access, like a faster, quicker access for small jobs, similar to the one of artificial intelligence that you've seen these days. So with these two mechanisms, you will have access to the 2 quantum computers and to the emulators that will be available soon, as soon as we take Mare Nostrum 4 out of the chapel. For those that were yesterday in the visit, or for those that will come today, you will see, you will know when where the 2 quantum computers will be placed as well. So just stay alert, we will make news in the web, but this will be the mode.
Thank you very much, Uriol. Okay, now it's time for questions. Anybody with something to comment, to ask, to share? Something there?
Thank you. This is probably more a comment than a question, and it's for Elias' comments during the talk. Igual me meto en un jardín tremendo. Yeah, I think I cannot disagree more on the perspective of looking at quantum computer just from the point of view of algebra. Yeah, I think algebra is cool, but physics is cooler. So, yeah, you know, imagine you go to the Pisa Tower with a steel ball and a piece of paper. You throw them away, and it doesn't matter how much algebra you put there, you will never discover the Newton laws. Okay, so I think it's probably true what you say, that, okay, I'm going to try to find common places between your perspective and mine. It's probably true that you don't really, it's not necessary to be an expert on anything related to quantum mechanics to like run something on a quantum computer right now. But I think that there are more layers. We are probably not still or yet there in the sense of, okay, now we have a supercomputer in CPUs or CPU-based or GPU-based, and there we can discuss anything about how to use it. But in quantum computing, we do need to develop new algorithms. I mean, there are many things to do. You perfectly know this. And you need to know more things. I mean, you have to develop some intuition to be able to think differently, like thinking in computer science or from the computer science perspective, the classical one, I don't think is very useful. So trying to, it's difficult to say, but I'm going to try to rephrase this. We should probably put more emphasis in new students and people learning now quantum computing to try to think differently, not recover the old frameworks or in this mental perspective, but try to think differently, because in many algorithms in quantum computing, you have to think differently. And you need more than algebra. This is what I was trying to say. It's more difficult, and I don't want to monopolize this question round. But yeah, trying to synthesize all my thinking.
Yeah, well, I completely agree that you need to think differently. I mean, I think that is the main difficulty of quantum algorithms. It's not really the math, it's how the math is applied. It's not very intuitive. It's not at all like you program a classical computer. But my point is that you don't need to know whether the qubits are implemented by ion traps or superconducting circuits or photons. You don't need to know what the polarization of a qubit is in order to apply quantum algorithms, even to develop new quantum algorithms. No more than you need to know whether your hard drive is implemented as solid state or magnetic, whatever. I don't know. I use my computer every day. I develop new algorithms. I don't know what is going on under the hood. So it's a layer of abstraction that I don't need to cross at all. Okay? And in quantum computing, I completely agree that you need to be aware of the underlying topology, for instance. Okay? Whether your qubits are all-to-all connected or are connected in a different way, this kind of thing. But you don't need to know the exact equations that govern the behavior of the qubits. That is my point. You don't need to know the philosophical implications of realism versus localism in the interpretation of the experiments of Bell or something like that, okay? But it seems to be a baggage that comes with quantum computing that, oh, you need to know a lot about quantum mechanics just in order to be able to understand a quantum algorithm. And this is something that I discovered when I started studying quantum computing, that is really not needed. You only need to know what is a vector, what is a matrix, what is an eigenvalue, things like that, that do not require this physical interpretation at all. I don't know if my point is clearer now.
Yeah, well, agree on the philosophical point of view, but yeah, if I do a proposal to use a telescope, I need to know the chip. I need to know, the more I know about the telescope, the better is going to be my proposal, for sure, even more. If I don't know the details of the telescope, my proposal will be rejected. So the more you know about the physical qubits that you have in your supercomputer will probably be, I mean, you will write your proposal better because you know the coherence time, which may affect completely to your algorithms. So you have to know that. I mean, you can tell me, well, I don't need to know that because somebody's going to tell me. Okay, right. Then we're moving the problem to somebody else, but the problem is there. So somebody knows to know that in the group or whatever, or around you. But you need to know that. You really know, you need to know that. And yeah, many other details. This is just an example. So yeah, okay, the philosophical point is right, you're probably right, but not the other things.
Okay, no, yeah. I think that the frontier is fuzzy, okay, of what you need to know and what you don't need to know. Probably in the future, I hope, this layer that you, the level of detail that you need to know will be higher and higher every time, okay? So you will need to know less and less about the underlying architecture. At the current moment, of course, you need to know the topology or decoherence times, this kind of thing. But this does not imply that you need to be an expert in quantum mechanics. You don't need to know how to solve Schrödinger's equation. You don't need to know about harmonic oscillators, quantum harmonic. I don't know. I really don't know. And you can use and develop new algorithms.
Okay, can I jump here? Yeah, sure. I agree and disagree part of what you say, totally. I don't think that's very different to what happens in regular computing. I mean, sometimes you are dealing with an algorithm and then some like super nerd will tell you, oh, if you change the flag of your compiler, whatever, and you are not aware of that possibility, it may increase your work, and having this depth of thought of what happens in the hardware and on the register level and everything may help your work. But and this is already happening in quantum computing, there might be people that are specialists on very particular areas, and then they can deal happily with that only, okay? So I think we are, of course, if you know everything, it's much better, but we can identify already some profiles where people may contribute positively to this field without having to go to this knowledge, which I think is what you were saying. and not what you were disagreeing about, okay? But just my point of view. I mean, that happens to me before knowing about quantum computer. And that, of course, you knew, okay, if I know more about the architecture I'm using, of course it would be better, but that's also an effort, and you have to measure that.
I think there are two different ways of saying that. I think the first point that you were mentioning is like, in order to understand quantum computing or to enter this field, depending on what you want to work on, you don't need to know about quantum mechanics or quantum physics. Actually, I have no idea about quantum mechanics or quantum physics. I started reading about that, and for me it was too difficult. I know the physics is right. It was like, wow. So you have to find where your boundary is, right? That's one thing, and you can stay in this level of just linear algebra and vector matrix multiplication, and for me, for example, that's enough. On the other hand, if you want to work in quantum computing, depending on the field that you are working on, for example, he works on quantum algorithms, I also work on quantum algorithms and variational, yeah? And I work on compilers and frameworks and programming frameworks and microarchitectures, and so I think the knowledge that we need is different. I need to know, for example, a lot of details about the technology itself. I need to know how the qubits are implemented. I need to know, yeah, and for you, maybe it's not that relevant. So then the boundaries are different depending on what, let's say, on what your expertise is and in what area you want to focus on. But the entry level, let's say, for understanding quantum computing is like, at least from an engineering perspective, is like, if you like to know about quantum mechanics and quantum physics, please go ahead and go into that. But you can stay like a couple of levels upper that one, right, and still understand quantum computing. I think that was maybe the point also you wanted to make.
So very quickly, I recommend a book from Scott Aronson, which is a computer scientist, called Quantum Computing Since Democritus. When I read that book, it was very surprising for me. I'm a physicist, so I came to quantum computing from a physical perspective, the hydrogen atom and so on. But he basically defined quantum computing from scratch without talking about the physics, only assuming that imagine that these are the rules of computation and you are allowed to do this thing. So how far can you go with all these rules, which are different from the ones from classical computation? And it was purely mathematical perspective, and he arrived to the same point. And then, of course, if you talk about how are you going to implement this in the real world, of course, you need to go to the physics and so on. And for algorithms, for instance, I like to work with near-term quantum computing, which means that you need a lot of information about the real device, coherence times, and it helps you a lot to know about the physics of the device. But then there are other people defining fault-tolerant quantum algorithms, like coherence times doesn't play any role there because we assume that is as infinite as possible in that sense, because we have quantum error correction, so we don't care about that anymore. We don't care about the errors because everything will be error corrected, so we just focus about what are the capabilities of that potential algorithm. So in that sense, I can see that you don't need to know about the Schrödinger equation because you are not evolving anything in time in your algorithm. But of course, the near-term part, for sure, you need physics. So depending on, as they were saying, the focus on your work.
Thank you very much. Is there any other question, any other comment?
Yeah, we only have time for one last question.
Okay, thanks, Alberto.
Yeah.
I can do a very short one.
Yeah.
A very short one. It's a very simple question related to the importance and the difficulties of multidisciplinarity for quantum computing, which is a buzzword that everyone talks about, but no one really knows how to articulate multidisciplinarity. So let me say that as much as a privilege it was to listen to these panelists, sometimes it seemed like a joke, in the sense that you had a computer scientist, a physicist, a mathematician, and a computer architect. They meet on a panel, they talk about this and that. So this was a multidisciplinary panel. So my true question is, how do you see, whenever you're articulating a research team, whenever you're creating a task force, whenever you're reaching out to community, so how important it is to have the multidisciplinary flag in mind?
I can start. I'm building a team of different people. It's difficult to make them, the language is very important, speaking the same language. So we have to have people with different backgrounds on different fields where we want to apply all these algorithms, but also the simulation is a very complex supercomputing problem, and then the physics, of course. Our approach has been having a team where we collaborate and everybody is a scientist. There's no distinction in this sense. And whenever we want to reach to a level of expertise, we go and look for external experts. We don't pretend to create experts on everything in-house. That's important for us. So in this sense, I like this movie, Armageddon, where they have to train some miners to be astronauts, while probably it's easier to train an astronaut to be a miner. So it's always this question. And I think we have to go to lower levels and start training people or get used to these languages or this interaction between different fields in a more early stage in their career, not when they are finishing their PhD.
Maybe I can also comment on that. I think that in this field, like in other fields, I guess, multidisciplinarity is key. You know, we are like at the very beginning of developing these kind of systems, and for within these full stacks, we need people from different disciplines, being mathematicians, any kind of engineer, physicists, of course, and you name it, right? So, but indeed, the most challenging thing here is putting all these people working together. Before moving to UPB, I was in Tilburg, in the Netherlands, for 7 years, working at QTech. The beginning, when I started there, most of the people were physicists, and we were trying to talk to each other, and we didn't really understand each other. I mean, when I said architecture, that is the picture I saw, for them the architecture is how to put the qubits in the chip, the layout, right, of the chip, and things like that. It was like, what? And they were talking also about different things that I couldn't understand. So I think it's key, as I said before, that we have these multidisciplinary teams in which we make the effort to understand each other and speak the same language. Only in that way we can really make progress and build a future quantum computer.
Yeah, I would only like to add that it's also important because of the applications. I think one of the main questions nowadays is what are we going to use quantum computers for in 10 years? And this is a question that we cannot answer from just a field. We need people from all over science, and not only science, to know what are the possible applications of quantum computers.
Very much. I would like just to close the panel saying thank you to all the speakers, of course, and just as Uriol has said, new quantum systems are coming to the res, so just stay alert. Thank you very much.